Some of you may be thinking to yourselves, I feel like I recognize this room. If you think you recognize this room, you do. If you don't recognize this room, that's okay. You shouldn't, but some of you will. Okay, yeah, so let's just see how this goes. Okay, so I don't want you to feel like you're just listening to the voice of God coming down from your speakers. So you're going to see me staring down at this piece of paper, but I also feel like sometimes it's helpful to have, not like that though, to have me on the screen, like as a person participating. Okay, here we go. So this is an example that I had for us to work in class that I didn't have time to get through, so I'm going to try to do this now. And this is going to be our test run, right? So I'm going to try to walk through this whole thing, giving you all my thought process. As you can see, I don't have any of my assess, want, analyze, any of that, but I do have a picture. So I'm going to walk through this whole thing, and hopefully you find this helpful. So what do we have? We have a hungry bear that weighs 700 newtons. So we have the force of gravity on the bear. So B is going to be bear is 700 newtons on a beam in an attempt to retrieve a basket of goodies hanging at the end of the beam. The beam is uniform and weighs 200 newtons. So the force of gravity due to the, I'm going to call this big G for goodies, is 200 newtons. And the beam is 6 meters long. It is supported by a wire that is at an angle of 60 degrees, and the basket weighs 80 newtons. And then what was this? Oh, that was the beam. Duh. Little b, beam, big G, goodies. How much do my goodies weigh? 80 newtons. So I need to do a force diagram. So I'm gonna not even go any further. I'm just gonna do that first, right? So I have this beam. I have a wall here. These lines mean that this wall is immobile. I have this box. This is my goodies. I have some sort of like supporting apparatus. And I have my angle here, and then do bears have tails? I don't think they do. Like if I think about the Jungle Book, Baloo, Baloo doesn't have a tail. I don't think bears have tails. Or maybe if they do, they're like little rabbit tails, where they're like little squishy cute things. He doesn't have arms or legs because I don't have that artistic ability. So I need to draw my force diagram here, right? So I have the force of gravity due to the goodies. I have some sort of tension force there. I also have some sort of tension force here. I have the weight of the beam, and because this is uniform, I need to put my force of gravity on the beam, like the weight of the beam, I need to put it in the middle of the beam, because instead of trying to figure out what the force is at like every single point along this beam, I can just assume that if I treat the center of gravity of this beam as where the force is acting, everything will balance out. Then I have no normal force, right, because it's not on the ground. And then I have the force of gravity of my bear. I think that's it. Okay. Draw a force diagram for beam. Did that. when the bear is at x is equal to 1 meter, find the tension in the wire supporting the beam and the components of force exerted by the wall on the left end of the beam. Okay, so I need this tension, and I need to find supporting the beam and the components of the force, okay, exerted by the wall on the left end of the beam. I need to figure out the force at this point. Okay, fantastic. So now I need to solve a problem. So I need to figure out what kind of problem this is going to be. So I know I'm going to have forces of some sort. So I'm going to use Newton's second law. Force is equal to mass times acceleration. This is Newton's second law. If you're going on to Physics 220, please remember that that is Newton's second law. Because, oh, this is a little lever thing, so it can move up and down. This thing can rotate about this axis, right? Because if I look at the actual picture, there's like a little hinge, so it can rotate about this axis. So because there's a possibility of rotation, I'm also going to have torque. So I'm going to use torque is equal to radius, force, and then sine theta, or it could be radius, force, cosine of theta. So if I want to figure out the tension acting on this rope, I could approach this with some sort of like force equilibrium. So I'm going to start with equilibrium of my forces. The forces in the x direction is going to be 0. Forces in the y direction are going to be 0 because I'm going to assume that this thing is at equilibrium still. So if I think about my forces in the x direction, I'm going to have this force exerted by the wall. That's going to be, so my summation of forces in the x direction, I'm going to have some sort of force exerted by the wall, and then the force of my bear is in the y direction, the force of the beam is in the y direction, my basket is only in the y direction. The only other thing that I have is going to be a y component of my tension here, and then I'm also going to have an x component of my tension here. So this would be plus my tension in the x direction, and this is going to be equal to 0. Oh, I figured out where this is going. I in my head, I just figured out where this problem is going. So it's asking me at some point in time to find the force exerted by the wall, and I also need to find the tension. This summation of forces in the x direction involves the forces on the wall and the forces of tension. So what it's going to have me do is going to have me solve for tension and then utilize this equation to solve for the force on the wall. But let's see where this gets us. So the forces in the y direction, we're going to have the tension. I'll put this back in blue. We're going to have the tension in the y direction. Plus we'll have the force of gravity of the beam, the force of gravity of the bear, and the force of gravity of my goodies. And those will all be equal to 0. Now, most of you are probably thinking, why don't I just solve all of this? Oops. Why don't I just solve all of this with the force approach, right? Because I have the force of gravity of my basket, I have the force of gravity of the bear, I have the force of gravity of my goodies, but the problem is that the tension on this wire is going to change depending on the location of my bear, and none of these have any dependence upon distance or position. So I need to take a step back and I need to approach this from a torque perspective. We'll end up coming back to these later, but in order to find my tension, my force of tension, I'm going to have to figure out how the weight of the bear and the location of the bear are going to affect that. Right? Because if you think about it, if you stand at different points, you could also think about like a diving board, right? If you go up a diving board, if I stand here, I'm apparently very short in this picture. If I stand here, the diving board isn't going to bend, but if I stand on the very end, the diving board will bend, so my weight is changing. Even if I had like some sort of rope there, my weight would be changing the tension on this rope. That's essentially what's happening here. So I need to now approach this from torque equilibrium. So the summation of all of my torques is going to be equal to 0. So I'm going to think about the torque in the x direction. No, we don't have torque in the x direction, at least. We just have torque. So I'm going to think about my torques, right? So before I do that, I am going to make that little chart thing. So if I need to think about the torque due to the bear, this is going to be RF. This is a 90-degree angle, so there will be no sine component because sine of 90 degrees is 1. So it's just going to be RF, and this is going to go in the negative direction. Then I have the torque on my beam. We'll have the same situation here. This is going to be RF, and it'll cause me to go in the negative direction. I need to think about the torque due to my goodies. And this is also a right angle, so this is going to be RF. It will also move us in the negative direction. And then I need to think about the torque due to that wire. I'm going to put here wire. And this will be RF. This is the force of my bear beam and Battlestar Galactica. Bear beats. Now it's stuck in my head. Bears beats in Battlestar Galactica. That's not what we're solving. We are solving for the bear, the beam, and the goodies. And this force due to the wire, that's actually going to be the tension force. And this is going to have some sort of angle. So it will be, I need this component of it, right? Because I need the component that is perpendicular. So the way that I'm going to solve this is I'm going to recreate this image here. So this is going to be theta. This is my tension. This tension in the x direction. This is going to be the tension in the y direction. I want the tension in the y direction. So it would be this component of it. So this would be so opposite. This would be sine of theta, and this will go in the positive direction. Okay, so this is now my little cheat sheet for my torque. So I have my summation of torque is going to be equal to the torque of the bear plus the torque of the beam plus the torque of my goodies. I don't know what letter that is. The torque of my goodies plus the torque due to the wire, and this has to be equal to 0 because it's in equilibrium. So now I'm going to replace these with what's on the other side of that equation. So I can now get rid of my summation of torque sign. So I will have R, these are different too. I'll just for these. off of the bare beam goodies wire. Okay. So I have the position of my bear. There's the force of my bear, and this is a negative direction, minus the distance to the center mass of the beam times the force of the beam minus the distance to my goodies, the force of my goodies, plus the distance to the wire, the force of that wire, which is tension, sine of theta is equal to 0. Since I want to solve for tension, I'm going to be solving for that. So I need to rearrange all of this. So in order to move these three to the other side, I'm going to add RBFB plus RBFB plus RGFG to both sides, RBFB plus RBFB plus RGFG. That will give me a new equation of R of the wire, is my force of tension, sine of theta is equal to RBFB plus RBFB plus RGFG. Now I need to get tension by itself, so I'm going to divide both sides by R sine theta, W sine theta. This is going to give me that my force of tension will be equal to, this is a mess of stuff, RBFB plus R little b F little b plus R my goodies times the force of my goodies divided by the distance to the wire sine of theta. Now I need to figure out what all my distances are, right? So the R of the bear is 1 meter. We know that. The R of the beam is going to be halfway to the beam. So the length of my beam is 6 meters. So this will be L divided by 2 because it's halfway, right? So this will end up being 6 over 2, 3. The distance to the wire is L, right? So that's the full length. And the distance to my goodies is also L. So that's going to be the full length. So I'm going to solve this now. It is going to be equal to 1 meter. I mean, if I'm recording this, I should try to model good behavior here. Times the weight of my bear is 700 newtons. Times 700 newtons plus the distance to the center of the beam, so that's 3 meters times the beam was 200 newtons plus the distance to my goodies, which is 6 meters times, how much do my goodies weigh? 80 newtons. 80 newtons. And we will divide that by the distance to the wire, which is still going to be 6 meters, and then sine of my angle, and my angle was 60 degrees. Great. Now we find our calculator. Since this is not an exam, I'm using the good calculator. 700 plus 3 times 200 is 600 plus 6 times 80 is going to be 1780 newtons per meter divided by 6 times sine of 60 is 5.196, let's call it 5.2 meters, which should give me a force of tension equal to 1780 divided by 5.2 is 342.3 newtons. And then I'm going to check my answers. And that is correct. We did a great job, everybody. So our force of tension is 342.3 newtons whenever the bear is 1 meter from the wall. Now we need to figure out what else we were supposed to do. We were also supposed to find the force exerted by the wall, and we can do that with this equation here. So I'm just going to write that Fw plus T equals 0. So we had tension force in the x direction is equal to Fw plus Tx is equal to 0. Fw tension in the x direction is going to be cosine of 60 degrees, and it will be going in the negative direction, so it'll be negative T cosine theta is equal to 0, so that means the force on the wall is going to be equal to T cosine of theta, and we have our T here, which is 342.3 cosine of 60 degrees, and we get that the force on the wall is 171-ish newtons. Great. So we have our solutions to part B. Part B. The next thing we need to figure out is if the wire can withstand a maximum tension of 900 newtons, what is the maximum distance the bear can walk before the wire breaks? So in order to do that, I'm actually going to use, let's see here. I think I'm going to have to use my tension, my torque again. I'll have to use this torque equation again. So I'm actually just going, can I just like take this and copy it, and then I'm just going to figure out how to work my, oh, it helps if I take it off lasso, right? That's helpful. Oh, let me just get the mouse. So I'm just going to reuse this equation for part C, right? So, how do I hide that thing? Control Alt Shift H. There it goes. Okay. So I'm just going to reuse this equation here for part C. So I now know that my maximum force of tension is 900 newtons, and I want to figure out how far the bear can go. So this is 900 newtons, and I want to find the distance of the bear. How far can my bear go out before my rope breaks? So to do that, I can set this equal to 900 newtons and solve for the distance of my bear, right? Because if the force, if the wire is going to break at 900 newtons, and I set this equal to 900 newtons, and I solve for how far out the bear is, assuming the rest of this is held constant, then it will tell me this is the furthest that the bear can go before the wire hits its breaking point. So I'm going to rewrite this RBFB plus RBFB plus RGFG divided by RW sine theta is equal to 900 newtons. I need to move this other to the other side, so I'm going to multiply this by RW sine theta. So that gives me RBFB plus RBFG B plus RGFG is equal to 900 RW sine theta. I am going to try to get this by itself, so that means that I have to subtract those terms from both sides. I'm going to skip that step because I already demonstrated that above. So that is going to be 900 RW sine theta minus RBFB. Nope, that's a minus RGFG. And then I need to divide by the force or the weight of my bear. So this equation will be 900 RW sine theta minus RBFB minus RGFG divided by FB. And, oh, moving away. Now I'm going to solve for RB, right? So this is 900. How far out was my wire? It was 6 sine of 60 degrees minus how far out was the beam? It was halfway if it's 6, so then this would be 3 times the force of my beam was 200 newtons minus my goodies were 6 meters out. Oh, I should be consistent. I should be consistent. I should be consistent. 900 newtons times how far out was the wire? 6 meters sine of 60 degrees minus how far out is the beam. I need to consider its center of mass, so that's going to be half of 6, so that would be 3 meters times the weight was 200 newtons minus how much of my goodies? My goodies were 6 meters out and they weighed 80 newtons, and I will divide that by the force of my bear. I forgot how much my bear weighs. My bear weighs 700 newtons. 700 newtons. And so what is the furthest that my bear can go out before this wire starts to break? So 900 times 6 times sine of 60 is, so this is 4676.5 minus 600. All of these are Newton meters minus 480. Oops. 480 divided by, these all have units of Newton meters, divided by 700 newtons, we'll end up with meters. That's good. So this is 4676.5 minus 600 minus 480 divided by 700. Hopefully it's not further than the beam, or we're in a pickle. It's not. Great job. So the furthest this bear can go out is 5.14 meters. After that, the wire is going to break. And that is our problem. I am going to go eat dinner now. Have a fantastic night.